Okay, this is step 19 for 3.2 connection design. Previously we stopped at step 18, column flange bending. As you can see, the top and bottom level of the column needs to be checked for the P-link. On the previous design, we checked the local capacities of the column for their corresponding capacities. Now, if the design is no good, then we add the stiffeners where is required. Okay, so the picture here shows two different ones. One of them is called partial depth, one of them is full depth. Partial depth is what you're looking at in the drawing here. The full depth goes all the way. Typically for one-sided connection, you could use a partial depth. We test it that way. Or if you have connections on both sides, then you need to go with a full depth stiffener. Okay, so full depth, partial depth for one side, full depth stiffener for two-sided connections. Stiffener design is for you take the minimum of the calculated capacity, so we get from web local yielding, web local crippling, and web compression buckling if you have double-sided connections. Okay, take the minimum of these and compare it to the PR of the link. If the minimum is greater than PR of the link, then okay, no stiffeners required. Else, then design for stiffeners for the force difference. And this is the key is you don't design it for the whole force of the PR link. You design it for the difference of force because your other components it's taking out some of the force. So you have some building capacity already. Okay, you need to check for capacities at the top and bottom of the beam. Step 8, assuming unstiffened condition. So, if your TF is greater than TF min, then okay. Step 18, assuming stiffened condition. If no good, then try another column. What I'm saying here is when you go back to step 18, they give you two conditions. One is stiffened and one is unstiffened. You start with the unstiffened one first because they give you lower capacity. If it doesn't check, then you add the stiffener. Okay, even after you add the stiffener, it still doesn't check. Then you have to go with a bigger size column. So that's what I mean by this here. Okay, step 19. Here are the design directly from the code report, the equations. You take the PR of the link, subtract the minimum of the VRN, and the minimum of the VRN is the design strength from 17, which is all these capacity. Okay, so you subtract that out to get your FU. Okay, for your stiffener design now, this is an example. We have at the top, at the bottom, okay, you're taking the maximum of these two forces. So this we actually have force difference of positive. This we have a force difference of negative.
The PR are the same.
Yeah, the PR is the same, which means we need a stiffener on the top. We don't need a stiffener on the bottom, right? It's greater than that. So we need a stiffener on the top only. And for our production, we want to make it consistent for different column. We're providing two. But for your design, that's special. We just need it. Yeah, we don't need this bottom stiffener. Okay. So that's what that means. So check tension yielding of the stiffener. So for design of stiffener, these are the steps. Check tension yielding of stiffener. Check stiffener geometry requirements. The geometry is typically given by the code and what it is. And then if it's a full depth stiffener, then we have to check for axial compression. After you have the geometry of the stiffener, then you size the welds to the column flange column flange on either side, or just one side for one-sided connection, and column web. So that's where the different steps. So 1, 2, 3, 4, 5. So let's start with the geometry first. I'm doing it backwards. Let's check 2, not backwards. Just find out the stiffener first, geometry first, then check for yielding of stiffener. So if I cut it out, that's what the stiffeners look like. So in order to fit it within, that's what they call the K area, this region. So you have to clip out the stiffener corner so you could fit it into that. So once you cut it out, all you have is this area. Okay, so that's the area that's attached to that. So but let's go through all the different clips for now. So for D1.8, there's a requirement that you take the clip from the K design. This is from the manual. You see there, they give you dimensions for different columns. You add 1.5 inches and you subtract out the thickness of flange. So this one's 1.9 inches. So we say let's clip this 2 inches. Okay, for a minimum clip, the minimum is just, okay, what is my K area and what is the thickness of flange? That's the minimum. This is per D1.8. Okay, D1.8 is assuming you don't want to weld in this K area. The K area is the region where what they do is to roll to, when they pull the steel shapes out of the long ones, sometimes they sag, so they have rollers that are in this area, this region. That's to strengthen them out. So if they do that, this area, there's some built-in residual stress. So if you weld to it, you might crack it, and they have seen cracking in some cases. So they discourage from welding to the K area, and that's why the 2 inch compared to the 1.5 inches for that clip. Okay, so they clip this much like that, and then you start welding. So you don't weld it to the K area region. This is a concern. The other one should not be a concern, but they still have, well, the requirement is a little less. You can see it's instead of 1.5, they say 1/2 inch away, and that's the clip on this clip flange. So it's 1.25. The minimum require is 0.618. Okay, so knowing what that is, now we have these two clips. Okay, how wide is this and how long is this? So the width is given by some equations in the code. So the minimum is from J10.8 is BF divided by 3, subtract half the web. So BF is this distance. They want you divided by 3 and then subtract half the width. So minimum cannot be less than that. Okay, a maximum, this is, okay, we don't want to, no, there's no maximum per se. You stick it out whatever you want, but we want it to be flush with at least the column flange. So that's why we call the maximum is the BF subtract out the TF divided by 2 is your width. So 3.57 minimum. So we call it, let's say, don't stick it out, just put in a little bit. So we call it 3.5 inches. The length required is really coming from some load. Make sure you're able to transfer your shear. Okay, so SMF number of sides. If you have 2 sides, then you times 2. If you don't, then you just take FU divided by, stiffener, and this is the stiffener yield. Then you plus or clip, right? Then you get a length required. So this length plus the clip, then you get this length. Essentially, that's what we're trying to say. Okay. Also, we want it to be no less than half the column depth. So this has to be greater than half the column depth. Okay, so that's for column depth 9.05 inches for half of that. So require is 3 point something. For our connection, because our FU are typically a lot less than your beam flange, because you're taking the whole flange to calculate FU. We're just taking the reduced one. We're using FU instead of FY, but typically ours is a lot less compared to the other connections. this one most likely will govern because half the column depth. So you can see this, the difference here is quite a bit. Okay. So that's the initial, what I'm saying, initial partial depth, initial full depth. If you need to use a full depth stiffener, all it is just full depth. You take the column depth minus the two flanges, that's your column depth. Okay, so you're trying to fit it in. Actually, whatever it is comes out, you should just call that number. I think it just rounded off to 8375. That's actually the length you need. If you call out full depth, it's for calculation purpose. For fabrication, when you take it to the fabricator, they will measure. They'll give you that depth because you don't want to be too short or too long. You cannot fit in there. For calculation purpose, you could round it down a little bit if you want. Now this is the length of the stiffener. So what I'm saying, and this is from MathCAD. I put in something. If it's one-sided, then you use the partial stiffener. If it's full-sided, then use the full depth stiffener. So since it's one-sided, we're using a stiffener, partial stiffener of 9.25. So the length of the stiffener is 9.25 inches. The width of the stiffener is 3.5 inches. The cut, I believe, this is 2 and this is 1.25. So that's what that stiffener is, just by geometry now. Okay, now knowing the geometry, we still have to check if it's good or not. Okay, so check the tension yielding. So tension yielding is, when we have the PR, and then subtract all the capacity, we have FU that's remaining. So each side is taking half of the FU. Okay, so that's what it is. Minimum area is FU divided by FY VT. Since we have 2 of them, and here's my B effective, subtract the clip. That's my minimum thickness or tension. Okay, for the minimum thickness per code, the AISC and our step 18.2. Remember, we say we don't want anything less than 1/4 inch. So the requirement, our 1/4 inch actually govern on this one. So we're saying use the minimum stiffener of 0.25, but on this one, and then the maximum is 0.5. So choose somewhere between the minimum and maximum. I just say, well, since we use a shear tap, all the plates are 3/8, I'm going to keep all the plates the same thickness. So when they order it, you could just cut it from the same thickness plate. So I just say order 3/8 inch thick plate. Okay, so that's the one-sided one. Full depth stiffeners, if you have 2-sided, then you need to do compression check. Compression check, however, the stiffener itself are not the only element that's resisting compression. Part of your web is too. So if you're looking down looking from this side, that's your stiffener contribution, and that's your web contribution for compression. This is for if you do the plate girder. That's what they're using for bearing, for stiffener, interior stiffener. They add the stiffener, but they also account for part of the web, and that's what's the interior, and this is obviously the end condition. Okay, so for ours, that's why it looks a little complicated. This is the stiffener area. 12 TCW is, we're assuming, at a end condition because we're near the top, so that's the area. That's for J10. So we get an area of a stiffener. Now you take the I of the stiffener, and then RD of the stiffener. We're doing AISC E2 check. We need the RD to find out the FE number. So these are all per the AISC equations. And when you look at it at the end, the DCR should not govern, or if you make it too thin, it might govern. So that's for your full depth stiffener compression check. After the stiffener is checked, now we have the size of filler well to the column flange. So this one is pulling on it by FU divided by 2. This is the well we're talking about. This, if you're pulling on either side, these are the wells we're talking about. So free well fillet is 0.75, 70 ksi. The filler middle, yep, thickness, and then again, anytime when you're welding, remember the minimum fillet weld required per the J 2.4. That you should always check that as well, because that's the minimum requirement. And then whatever is required, then you calculate it. So for this one, half of the FU, and then divided by fillet, divided by the 1.5 times 0.6 FEX. The 1.5 you could ignore if you want. Remember, you get the strength increase if you're pulling on the shear versus the 0 degrees versus 90 degrees. That's where I think the 1.5 that 1.5 comes from the 0.6 FEX, and then we're only looking at this, so we have to subtract out the clip flange, and now times the root. This is basically at the end. That's the size of the fillet weld we need. This is what you should be calling out minimum, because that's greater than that. For ours, our fabricator wants to be use all pretty much one size weld if possible. Like, they don't care if it's just a little bigger, because for their guys, they want their weld all the same. That's not just cost savings, it's more of a quality control. For the welders, all they do, oh no, I'm doing a Simpson connection, 1/4 inch weld is all I do. So that's pretty easy for them. So on this one, I say 1/4 inch. Okay, we could actually use 3/16. That's the minimum we use. The DCR for this one is 0.5 or 0.45. So use double-sided fillet, 1/4 inch fillet weld. So one here, one on the bottom. Just to point out one thing, on this one I have not subtracted out yet. A lot of them typically don't like to weld all the way to the end, or weld all the way to the end, and they leave like a 1/2 inch either way. So you might want to subtract out after the clip, subtract out another inch. Like when you see this weld here, they don't go to the end. So we're counting on the whole width. So you'll need to subtract out this each side. I would say one inch. So half an inch on either side. Okay. This is the double-sided fillet to the column web. So these are the welds we're considering. Very similar to the flange. Again, you have the minimum weld size. The minimum weld size didn't change because the plate thickness didn't change. The column web one, again, is I did not subtract out the no welding here. Some like it to leave, again, 1/2 inch. They don't like to weld it to the end. So if you want to subtract that out after the weld clips, the web clips, you can subtract another inch. Then you get the size. So again, this one is 3/16. We're saying, okay, that's 3/16. Ideally, again, this would be a 1/4 inch for them to. But I just want to show the difference. That's minimum, then you could actually specify the minimum. But engineering judgment. Anyway, review. This is actually a long one. And that is a connection. I mean, whatever you see on this presentation, that is a connection, how to put together a connection. I'll go into some detailing regarding tolerances or placement and all that later on. But this, you know how to design a connection already. So again, step one is, or item one is a connection design using the capacity design approach. You calculate the ultimate capacity of a link, the reduced area one, then design all components to be greater than that. As you can see, every step we have to compare to the PR link. PR link. So check panel zone shear capacity first. Okay, like I said, this check does not require analysis from SAP. Remember, we just drop down from the Excel. You can see the thickness. So choose size where panel zone checks before you do the SAP analysis. Okay. Out of the beam connection, ferry mode, shear tap center bolt, and horizontal beam web bolt bearing will most likely govern, because we're only counting on the bolt 1 bolt. Flange local buckling do not apply to our connection. They're the one where it's welded, so you don't have to worry about that with the J 10.1. The web compression buckling check only requires for two-sided moment connections. Stiffener compression check only requires for both-sided compressions, where you have moment coming in both sides. Stiffener design for difference of the PR link and the minimum of the design strength for 17. So design it for the force difference. That's it. So that's wrapping up the connection design for our Simpson procedures.